Good afternoon, everyone. It's my great pleasure to introduce the next speaker in the colloquium, Cedric Villani. It's a great privilege. It's also a great challenge because the scope of Cedric's activities is nothing short of breathtaking. I will try to summarize in just a few minutes. Cédric is, first of all, the perfect example of the best that the French science and education system has to offer. He was a student at the Lycée Louis-le-Grand, then at École Normale Supérieure, and then he went on to get his PhD from Paris Dauphine under the supervision of Pierre-Louis Lyons. He became a professor at École Normale Supérieure in Lyon, then at University of Lyon, with the parenthesis during which he was the director of the prestigious Institut Henri Poincaré in Paris from 2009 to 2017. His scientific work is focused on partial differential equations and statistical mechanics, and in particular, his work on Landau damping and the Boltzmann equation earned him the Fields Medal in 2010. Cédric collects many other prizes and distinctions, and it would probably be a bit too tedious to go through the list. So let me just mention the Joseph Doob Prize for his treatise on optimal transport, Old and New, which is perhaps the ultimate book on the subject on which Cédric also worked. He is, in parallel to that, one of the great communicators of mathematics of our time, and he does that in many dimensions. As a lecturer, I remember in particular the first time I met him in Lisbon almost 18 years ago at the International Congress of Mathematical Physics, where he gave a plenary lecture, and more recently at the International Congress of Mathematicians 2018 here in Rio, where we benefited from a beautiful general public lecture given by Cédric. He's also an author, and the Brazilian Math Society published recently the Portuguese translation of his book, Théorème Vivant, Teorema Vivo, which provides a very rare, unusual glimpse into the soul of mathematicians as they do what they do. The book has been published in several languages by now, and as I said, including in Portuguese by the Brazilian Math Society. Perhaps even more surprising, Cédric is also the author of comic books. I have in particular a copy of his Ballade pour un bébé robot, comic books, bande dessinée, which Cédric kindly gave me a few years ago. He also plays a role in scientific innovation as a scientific manager. He used this stint as director of Institut Henri Poincaré to very actively promote innovation in scientific communication, the use of new tools, and a better, more effective way of reaching the society as a whole with the message of mathematics. Of course, in addition to all that, Cédric displays a very dashing public figure, which makes him the darling of the media communication vehicles, which turns out to result in benefit for the mathematical community. We have a herald of mathematics in Cédric. In addition to all that, and rather surprisingly, a few years ago, he very famously decided to take his public role to a new stage by engaging in politics. And he has been doing so for quite a few years now with a lot of success too. And today he is back on his mathematician's hat to lecture to us on convergence to equilibrium through reversible mechanisms in classical mathematical physics, known and unknown. Please, Cédric, and thank you very much for accepting our invitation.
Thank you very much, Marcelo. Thank you for the invitation. Thank you for the way too kind presentation. It's always a pleasure to be lecturing. For me, having been occupied by political issues so densely over the past months. It's a real pleasure to have this conference here fully about mathematics. The themes that I will talk about in this lecture are themes on which I've worked for years and years, and I will try to present it in a way that is as synthetic as possible, with some attempt of unified overview of our research spanning a number of years, and also in such a way that hopefully some of you guys may take home some ideas that may be used for your own purpose, who knows. So let me go and share the screen. Can you see the screen? Okay, hopefully just a second.
Yes, yes, we can.
Okay, there we go. So today is about convergence to equilibrium through reversible mechanics in classical mathematical physics, known and unknown. Sorry for the slight mistake about the date. Was assumed to give the lecture a few days ago, and then there was a misunderstanding only due to me, which I am very happy to be able to repair today. As we know, long-time behavior is so important for a number of reasons. We have to predict observations, and in particular, in many cases, stable behavior is the one that is obtained in large time behavior, is the only one that you will be able to observe in real life. Also, for most equations, we don't have a closed formula for the solution, and then say something even when there is no formula for the solution is essential. And let's all remind that large time behavior is difficult even for classical systems. So my talk will be entirely focused on classical system. Let me remind you that the oldest of all such problems is the stability of the solar system. It's the most famous. Its history spans hundreds of years, and it goes back to the Newton equations, say for point masses. This is a simplification. So you have x, which is a vector, depends on time. There are as many such unknowns as there are planets. There are the masses of the planets and the sun. You have the equations of Newton, second order differential equation. This is the universal gravity equation. And when you have only two bodies, this goes back to the Kepler equation, and it's explicitly integrable. When you have more than two bodies, there you have the stability problem, which is most famously known as the solar stability problem. Is the solar system stable? And let's summarize hundreds of years of research on this problem in the following slide. Okay, of course, you can ask the problem more generally for a number of interaction potential, W interaction potential, not necessarily gravitational. What do trajectories look like as t goes to infinity? How does the system look like as t goes to infinity? As we know, the solar system is perturbative, as is very well recalled by this striking picture in which we see that the solar system is the sun plus a tiny perturbation. The tiny perturbation comprising all planets is maybe of the order of 1/1000. So let's call epsilon our small parameter. Mass of planets divided by the mass of sun may be of the order of 10⁻³ In the 18th century, great mathematicians of the past have proven that you have stability of the distances between sun and planet over huge times, like 1/epsilon², okay, in the absence of resonances, etc. Then Poincaré, in this epoch-making article, first believed that he proved the stability for very large time, and then understood that actually he had proven the possibility of long time instability, and devised a number of new methods and theories which gave rise to modern theory of dynamical systems and ergodic theory and so on. In the middle of the 20th century, Kolmogorov had the genius idea that a slightly perturbed integrable system remains most often, in the sense of probability, quasi-integrable, and so that trajectories should be with high probability distortions of the integrable trajectories and thus stable for all times. And later in the 70s, 80s, Laskar and then Tremaine gave evidence that behavior of the solar system is actually chaotic. And this was done by numerical simulation, which came with a lot of theory about the numerical analysis and very clever methods to do so. So over a few centuries, the dominant mood of the scientific community on this problem has swung 4 or 5 times about whether it's stable or unstable. To this day, we still cannot answer this mathematically speaking. We have the numerical simulations, we have some insight about them, but it remains one great frustration for mathematical physicists to not have some understanding of really what is going on and how to tackle it, and whether it's a curse or not. That is the situation for finitely many bodies. That is the situation for the solar systems. And from that peculiar problem, 2 extremely important paradigms have emerged. The first one is the idea of ergodicity. You have a classical mechanical system, you list built-in restrictions like conservation laws, you list everything that is symmetry or whatever that you may think of that constrain the system. And when you have listed all the constraints, you hope that all the admissible phase space can be attained, and then replace large time averages of trajectories by phase space averages with respect to an equilibrium measure, which hopefully are much easier to compute because this is a static problem, say geometric, and not a dynamical problem. That is the paradigm of ergodicity. And another kind of orthogonal paradigm is the Kolmogorov-Arnold-Moser theorem, or theory of philosophy. You take a completely integrable classical conservative system, Hamiltonian. In the solar system example, this would have been the system with no coupling between the planets, so independent periodic trajectories of planets interacting with only the sun. You perturb this system by adding a small non-integrable interaction of very small size. And then with probability very large, that is when epsilon becomes very small, probability becomes very large, the system remains stable for all times and trajectories are deformed quasi-periodic when you view the system as a whole. This is another paradigm. Sometime when you're lucky, you may find that the system is ergodic or has some ergodic features. Sometime when you're lucky, you may find that the system behaves like Kolmogorov-Arnold-Moser and that you may integrate it in some sense in this way and then understand the large time behavior. Application to real world is very frustrating. Ergodicity works better if the system is well mixing. This was understood very soon. But then what are the mixing systems? There are some classes, there are some systems known to be ergodic, but very few realistic systems are known to be ergodic, and it's known that many are not ergodic. Kolmogorov-Arnold-Moser, which says philosophy that even if a catastrophic behavior a catastrophic behavioral system is not forbidden by conservation laws, it may never happen, this catastrophic behavior, and system may behave quite nicely. So it's very, very striking. On the other hand, it never applies to real systems. Perturbation which is required is so small that it's never satisfied in practice, and it's only for very special systems, near integrable systems. So it's very striking from the philosophy or epistemological point of view that Kolmogorov-Arnold-Moser was such a revolution, and it was, there is no doubt about this, even though in practice you can hardly find any systems to which it may be applied. There is an interesting paradox in there. This is just a shortcut for hundreds of years of fascinating research for finite dimensional dynamical systems. Now, what happens when you're interested in the stability of a galaxy, of a gas, of a plasma? and then you don't have 10 bodies, but you have billions of bodies, or billions of bodies. How do you handle this? Forget about the idea to apply the theorems of differential equations in this huge dimensional space. It would be a nonsense, both practically and theoretically. Then go to a system with infinitely many dimensions, partial differential equation rather than differential equation, and wonder what to do about it. Large particle system, this is the revolution at the end of the 19th century with the works of Maxwell and Boltzmann, and then a number of followers. Forget about individual particles like xi or xi derivative, and focus on the particle density f of tx v dx dv in phase space, which counts, so to speak, the number of particles in a dx dv element of phase space, x and v for position and velocity. And when can you write an equation on this particle density? There's a basic principle in statistics that the statistical behavior of a crowd of n particles is predictable if individuals' behaviors are uncorrelated. That is, if you take two particles or two atoms or two electrons or two stars or whatever it is that you have in your system, when you look at the trajectories of two of these among the crowd of n, it's as if these two particles would be independent of each other. Or maybe at some point they will interact and then become dependent for some time, but then they will separate and later they will be independent. And this statement of uncorrelation is equivalent to say that the density of particles satisfies a deterministic evolution, and then you have a closed system on your particle density. There's a whole variety of models about this. The most famous is the Boltzmann equation. It describes dilute gas, like high atmosphere. Then second most famous is the Vlasov-Poisson equation in plasma dynamics, of huge importance for practical and theoretical reasons in plasma dynamics. And then these are electrons. The most important feat dominating the equation is the dynamic between electrons. And this is Coulomb interaction. Vlasov-Poisson equation also is important in stellar dynamics, but these are not electrons, these are stars. And the force is not the Coulomb, but the Newton interaction. And it's fascinating to discover that it's the same equation which is applied, in which particle stands for star on the one hand, or particle stands for electron on the other hand. Of course, the sign of the interaction is reversed, and then there are a number of differences in the properties. Many properties are the same, many properties are also different between stars and plasmas. And then you have a whole zoology of degenerate dissipative equations with friction or collision terms or whatever, and also a whole class of fluid mechanics. In two-dimensional fluid mechanics, there's this symmetry which is well known, which says that the vorticity is transported by the flow, and then it becomes as if you had tiny particles of vorticity which are transported. So it can also be recast as a density equation, in which is the statistics of vorticity, which is here. Vorticity in 2D being just a number. Okay, for all these models, equations and situations of long-time behavior have been studied and restudied. Let me recall the most important common culture of these results, but first insist. These infinite dimensional equations are much more sophisticated than the finite dimensional dynamical system, but they lead to much more structure and tools. So in a number of situations, even though it's infinite dimensional, you have some road or at least some plan that you can try to follow using different tools from analysis, and a number of tools which you do have in infinite dimension and which you do not have in finite dimension. This is Vlasov equation. How to read this? Time differentiation of the density function. This is the transport term. This term is here to remind us that particles like to go in straight lines when they don't collide or don't interact. And this is the force field which is generated by the particles themselves. And it deviates the particles, so it modifies the velocities. Here we see that positions are modified primarily by the effect of particles going in straight lines, and then velocities are modified. This is the force acting to differentiate, to change the velocity through the Newton equation. And this is a nonlinearity. Particles, they all move in the force field which they create themselves. This is the standard equation for all of plasma physics and for a number of other phenomena. Let me remind that already here, the rigorous justification is still open for realistic interaction. By this, I mean for Coulomb interaction. Nobody knows how to rigorously prove under reasonable assumptions that a number of particles interacting in a Coulomb way, when you take the limit n goes to infinity, it does converge to the solution of the Grasov equation. As you see, the plan seems already at step 1 to be extraordinarily difficult, and that is the case. And this has to be counted as one of the emblematic open problems of mathematical physics. Let's continue. More elaborate problem is the model is the Boltzmann approximation when you add collisions. And this takes into account the fact that from time to time particles come very close to each other, and then there is an interaction which is at a level which is not the mean field level, but a much smaller level. This leads to an additional term, usually written as Q, and this is a Boltzmann collision operator. It's quadratic, modeling the effect of binary collisions, only binary because the gas is dilute, and so ternary collisions don't count so much. The justification of this operator is better than that for the Boltzmann equation, in the sense that Lanford's theorem and its recent improvements do provide justification. However, let's insist, only in small time if you are in a confined geometry. This also, large time derivation should be considered a major problem. Boltzmann and Grasov equations are pillars of kinetic theory. Here are 3 beautiful books based in large part on them. And they are also archetypes, these 2 equations. Through the study of these equations, you hope to deduce some effects which are useful in many physical situations. So how does it work? The most important theorem in the Boltzmann equation theory is the H theorem of Boltzmann. You look at the uncertainty S, or entropy, which is associated with the macroscopic distribution, f of xv. There's a formula for it, which is minus integral of f log f. It can only increase with time. You can compute the time derivative. The integrand has the structure of a minus b log of a divided by b, which is non-negative, and vanishes only for some very special distributions, Gaussian distributions, with a particular covariance matrix. This is the H theorem, so famous because it leads to irreversibility as time goes. Here is the picture that at the beginning of 20th century looked to be natural between Grasov and Boltzmann equation. Grasov equation, the mean field equation, is time reversible, while Boltzmann equation is time irreversible. Entropy is constant on the Grasov, entropy increases for the Boltzmann. Energy being constant in both models. There are variants with non-constant energy, but let's keep on the constant energy. For Grasov, there's a whole wealth of equilibria. For instance, any distribution which depends only on the velocity is an equilibrium, and it's just a particular class of equilibria. There are even much more. On Boltzmann equation, very few equilibria, only Gaussian equilibria and they have to be with constant parameter, constant density rho, constant temperature T, and uniform equilibria. So all of this suggests that entropy increase stabilizes the system, that for the Vlasov equation, you don't really know what will occur or how the system will select an equilibrium, a whole variety of behavior possible. And for Boltzmann equation, on the other hand, stability by entropy increase and convergence eventually to the Gaussian equilibrium. And how to see this convergence is by studying the entropy increase, which is manifestation of the dissipativity or the irreversibility. And how to study long-time behavior on the Vlasov equation may be looking more like a classical dynamical system. This is what the situation, how it looked up to the 1930s. Now, the whole purpose of this talk, because I go more in detail, is to insist on this, and this is the only slide that you may take home. Reversible mechanics may also stabilize, at least in two different ways. By reversible mechanics, I say the transport part, the part which is conservative, the part which is entropy preserving. That part may also stabilize. First, it may enhance a degenerative dissipative mechanism, so that there will be a combination between the reversible and the irreversible part, and the combination may be much stronger than just the irreversible part to drive the system to equilibrium. And the second mechanism is by phase mixing, the reversible mechanics may damp out inhomogeneities. Phase mixing is this phenomenon in which, say, your system is mixed through an incompressible flow in phase space, and there is the tendency to have initially well-defined forms distorted into filaments, which may become stripes, which may become blurring, and this is the phase mixing which may damp out inhomogeneities. These two phenomena, I will summarize them and give you some ideas of the tools we used for this, but each of them in the recent years has kept mathematical physicists busy for 1 decade. Let's say this first phenomena, it was very active from 2000 to 2010. The second one from 2010 to now, with a number of works and tools for this. And this is the sequel of the slide. So the only thing you may take home. First, both phenomena are observed and measured in real world, and both in theory and experiments. Both are geometrical features influenced by the geometry, the boundary conditions, et cetera, et cetera. Both may be proved, at least in special geometries, mathematically speaking, rigorous way, preferably in fully Eulerian formalism. You know, you may follow particles, and that is a Lagrangian behavior, or you may follow the flow, and that is Eulerian formalism. And often it's good to go back and forth. Actually, when you can go fully Eulerian, it's more flexible, it's much better for the adaptation. And they may be proved through functional inequalities which involved densities, velocity fields, sometimes with logarithmic terms, sometimes with L2 norms, sometimes with regularity norms, and so on. Norms and distances tailored to the dynamics, sometimes extremely complicated, but which you have devised very carefully to be adapted to the particular equation you're looking at. And also through toy systems of differential equations, which capture in finite dimension the main feature of the irreversibility or interplay between the reversible and irreversible part. Smoothness is involved in this, subtle smoothness estimates, and it's not an artifact. Smoothness is important, and some of the optimality results show in particular that some regularity class that seem to be very particular, like Joubert regularity, play a natural role, in particular in the damping. And this can be studied on various time scales. In particular, when you look at a small parameter, a bit like in the perturbation setting for the solar system, sometimes you have a small parameter, which may be a force, which may be a perturbation, which may be a viscosity. And then you ask, on a certain time scale, I have the damping. On a certain time scale, I have the regularization. On a certain time scale, I have the convergence to equilibrium. And you may study all these phenomena depending on the time scales and on the smoothness. And that is what I will describe. So the rest of what will follow will deep a bit more in some of the tools, some of the most robust tools which have been discovered over the past 2 decades for this. But really the whole philosophy is summarized in these 10 lines. First, some simulations to get an idea of what may be going on. This is the Boltzmann equation in a very simple geometry, simulations by Francis Philbé, in which he's looking at the simple geometry, and he's interested in 2 features, which is the degree of inhomogeneity in the Boltzmann equation and the convergence to equilibrium. So here he's plotting the H function in logarithmic scale. So it goes down, the entropy goes up, the H function goes down, it's the same. We see that it's roughly a line, so this is roughly an exponential decay. And here, this curve here is the H function relative to the so-called local hydrodynamic state. So the only thing you have to take home is the fact that when the 2 curves are very close to each other, the solution of the Boltzmann equation is almost spatially homogeneous, only depending on the velocity. And when they are separated, it has a huge dependence on the position variable. What you see in these 2 situations is that depending on the geometry and the conditions, you may have a solution that becomes quickly almost homogeneous, or on the contrary, solutions which have inhomogeneities that continue to go on and fluctuate. This kind of fluctuation is an effect of the reversible part, of the transport part, not of the entropy part. But on the other hand, without the interplay between the transport part, which is reversible, and the collision part, which is irreversible, you would not have exponential decay at all. Decay would be much slower. Here are some simulations of what occurs in the Vlasov equation and that so-called Landau damping. Completely different situation. What you see here is a typical behavior starting from a stable homogeneous equilibria in the Vlasov equation, send a small perturbation in velocity, and see how it evolves in time. You see these huge oscillations in velocity. This is an effect of phase mixing. It's an effect of the reversibility. It seems that it does not go to equilibrium, but when you average and look at the gravitational energy, for instance, or electric energy, you will see the decay. Again, this is in logarithmic scale. At the same time as the solution oscillates more and more in velocity space, the energy decays exponentially fast. This is the damping, and which shows you that there is some decay and wiping out inhomogeneities. Boltzmann equation. Here's an old result, 2005. Devido and I proved that if you have a uniformly smooth and positive solution of the Boltzmann equation, then you have convergence at least faster than any inverse power of time, and decay bounds can be estimated from smoothness and positivity bounds. The rate was improved by Gu and Strain to show that convergence to equilibrium actually is exponential. Okay, depending on which potentials you are looking, it may be a fractional exponential. Let's explain a little bit how it's crucial that such a theorem uses both the irreversible and the reversible part of the equation. Our method was based on 4 first-order and second-order differential inequalities coupled by functional inequalities, using lower bound on the entropy production far from hydrodynamic states, instability of the hydrodynamic approximation in presence of gradients, that is a fluid mechanics input, some geometric inequality like Poincaré or Korn inequality, and the study of the system of differential inequalities, Grunwald style, even though it's 4 coupled equations, plus interpolation in which you trade smoothness for exponents. Let's see how it works. First, what is a hydrodynamic approximation? When you go from Boltzmann equation to fluid mechanics, you forget all the fine details of the profile of the density, and you retain only a crude Gaussian approximation to the kinetic equation. Gaussian with parameters that may depend on the position. Temperature T that may vary from time to time. Density rho that may vary from place to place and from time to time, of course. Temperature also may vary from place to place. And mean velocity, which is like the velocity of the fluid, which may change from position to position. So that guy is the best approximation of this guy by a hydrodynamic state in which only density, temperature, and velocity remain the relevant variables. And there's a recipe which is like a projection to go from the kinetic distribution F to the density, to the mean velocity, to the temperature. These hydrodynamic approximations, if you're studying the approximation, is your best friend. If you study the convergence to equilibrium, is your nightmare, because they make the entropy production vanish. So the dissipative part is degenerate whenever the distribution becomes hydrodynamic. Entropy increases 0 at that moment, and then you lose any hope to have a good estimate on the rate of convergence. So how do you overcome this? Studying the entropy production. Entropy production, let's call it D, like dissipative term. It will vanish whenever the distribution function coincides with the hydrodynamic approximation. But you may hope to have a lower bound which depends on the distance between the kinetic distribution to the approximation. That distance, you may express it in terms of entropy, of difference of entropies. That is always positive. And you may prove, depending on regularity, on positivity, etc., that you have here a coefficient as close as you wish to 1 in the exponent. Okay, so this inequality is a functional inequality expressing the degenerate dissipativity of the Boltzmann equation. Dissipativity because it shows that something is always positive, entropy increases, but degenerate because whenever F becomes close to hydrodynamical, this quantity becomes very small and you can't extract any information. To overcome this, you need to use the conservative part, even though the conservative part in itself is entropy preserving. So you have some geometric feature to use. How do you do it? This is a system. Take it a bit in an impressionistic way. Don't try to catch every detail. The first system is the dissipative equation. It shows you whenever I am far from being degenerate, from the, let's say it's kind of infinite dimensional degenerate manifold, then entropy production is good. Entropy increases. I get closer to equilibrium. And this is quantified by this inequality. Then it may occur that this quantity is very small, so that F is very close to hydrodynamical. Then here comes the second differential inequality. I look at the L2 norm between F and the approximation, which is the hydrodynamic state. Whenever this quantity becomes very small, I'm in trouble. And I want to see that it will rise again. So I look at the second derivative, because it's a quantity that is positive, comes very close to zero. I want to see that it will become positive again at later times. So second order derivative is the right one. And I can see that up to a bunch of errors that will be controlled later, it is positive as soon as there are gradients in the temperature which I can use. And that is the key. Whenever there is some inhomogeneity in the temperature, second order differential equation shows you that this quantity will rise again. It will feed again in the first equation, and your entropy will increase again and again. Now, it may occur that the temperature gradients become very small. Then you will use the third equation, and the third equation, etc. So it's as if you have a sequence of differential equations all expressing the various degeneracies of the system. Okay. And then it's a matter of understanding how to handle this Capel system of equations. I will not say more about that system. Let me quote Harold Grad, specialist of Boltzmann equation, very active in the 50s, 60s. The question is whether the deviation from a local Maxwellian, which is fed by molecular streaming, this is the conservative term, in the presence of spatial inhomogeneity, this was like my integral grad t square term, is sufficiently strong to ultimately wipe out the inhomogeneity. So a valid proof of the approach to equilibrium requires just the opposite of the procedure that is followed in the proof of the H theorem, Videli set to show that distribution function does not approach too closely to a local Maxwellian. Okay, this is from a very inspiring paper by 65. Very inspiring, even though there are a number of mistakes in it. In a memoir, a few years later, I tried to isolate general principle and situation in which a conservative part and the dissipative part are in such a configuration that the conservative part alone does not induce relaxation and the dissipative part is degenerate but not sufficient, but combination of the two leads to relaxation. There's an analogy with the hypoelliptic theory in which you have first order part conservative, second order part dissipative. First order part in itself does not induce regularization, second order part is degenerate, but the combination leads to regularization. And in the memoir, there's a number of theorems with some interplay between hypoellipticity theory and this, which I call, following suggestion by Thierry Gallet, hypocoercivity theory. It's like we want to prove the coercivity with the interplay of the conservative and the dissipative parts. So this is the most famous theorem in hypoellipticity. You have a sum of squares plus a derivation, theorem of Hörmander, and you look at the associated partial differential equation. If the rank of the matrix is maximal, then you have infinity regularization. So you see this with the interplay, you see this for the rank which is obtained by taking the commutators between all the xi's and xj's. That is the theorem, the right theorem is here. Elliptic case, sorry, was the case in which rank is maximal. The hypoelliptic case regularizing is the case in which you have maximal rank by taking into account not just the vector fields, but all the algebra which is induced, the Lie algebra which is induced by the vector fields. So finite number of commutators involving dissipative and conservative part. If it generates all directions, then you're good. Here is an example of one of the theorems which I proved in this memoir with this interplay between the conservative and the dissipative part. It's an abstract linear result in a Hilbert space. Call it A star A plus B. With this is obviously the dissipative part, and this operator such that B star is minus B, so it's anti-adjoint operator, is the conservative part, say on your Hilbert space for evolution. Now, take L to be A star A plus B, okay, and define a sequence of commutators, chain of commutators. C0 is like A. Take commutator with the conservative part. This gives you commutator of the next rank, maybe with some remainder, which you will control using some assumptions, etc. And if, okay, these assumptions, forget about them for the presentation. This is to say that you can control some error terms. If the sum of the Cj star Cj is coercive, then you have exponential convergence in a norm which is equivalent to a L2 Sobolev norm of order 1. That assumption is the exact analog of the Hermander condition of full rank when you take the commutators. But it's not a finite dimensional assumption. It's coercivity of the sum of the Cj star Cj. Here's an example of application to the problems of kinetic theory. So take a linear equation. This part on the left is the same as the Vlasov equation, but it's the linear one in a given vector field. And on the right-hand side, you put some diffusive part, diffusion and friction only in the velocity. So this part is degenerate in velocity, but diffusive. And this part is conservative. This is your A star A in the right Hilbert space. And this is your B operator, skew symmetric with respect to the equilibrium. And now assumptions of the theorem are satisfied as soon as the second order derivative of the potential does not grow too fast, and as soon as the exponential minus V does satisfy a Poincare inequality. So in the X variable, some coercivity. Then you do have the exponential convergence to equilibrium. The proof is constructive, and it's all based on devising the right norm to analyze this. What kind of norm? The core of the proof is a Wright-Lyapunov functional, which is of Sobolev type. This is in the simple case how it will be. L2 norm, and then you have like an H1 norm Sobolev type with derivative in one direction and in the other direction. If I would write just this, it would be a usual Sobolev norm. Derivative in X, derivative in VC. And now I will put another term, which is a scalar product of the two derivatives. That other term is small in the sense that B, the coefficient here, is much smaller than square root of AC, where A is the coefficient here and C is the coefficient here. Actually, that norm seems to be stupid because it's equivalent to the first one. It's a Cauchy-Schwarz inequality. You have just an equivalent norm, you have added the lower order term. They are equivalent, both norms, in the sense of functional norms. But they are quite different when you look at the effect under the dynamics, because the conservative part will take the lower order term and transform it into a term that is dominant in some sense, with a key algebraic identity, and that is where a commutator will come. And when the conservative part acts on that lower order term, there will be a positive term in the direction which you want to gain that will come here. Okay, let's not say more of about this. Okay, then I worked out a number of other theorems, for instance, for Boltzmann equation in the context of fully nonlinear equation. One with a conservative part, dissipative part, in a scale of interpolation spaces, which may be Hilbert spaces and which kind of mimic the role of the ladder of functional spaces that are used in Nash-Moser theory or proof of Kolmogorov-Arnold-Moser theory, etc. And theorem can be applied to Boltzmann equation, etc. Let me just show you the functional, the Lyapunov functional in there. Okay, here is Lyapunov functional. This is to show you that in this kind of results, you should not refrain from putting enormous complexity in the choice of the Lyapunov functional as long as you know where you're going. Lyapunov functional may be extremely sophisticated. In the end, it will always be equivalent to the usual one. For instance, this one is equivalent actually to just the entropy if you have smoothness bounds. All the other complicated terms are negligible, but they are the ones that will act well when you put the conservative dynamics. Now, exploiting the phase mixing is another story. This was about, as I told you, is talking about unified survey of two important phenomena of conservative parts, one which is enhancing the dissipative diffusion, and the other which is damping by phase mixing. In the 1940s, Landau discovers something which was considered as amazing at the time. If you take the nonlinear Vlasov equation and you linearize it around an equilibrium, which depends only on the velocity, for entire analytic data, the force often damps to zero as t goes to infinity. Why was this considered amazing? Well, because it's conservative equation, the entropy is preserved. There was considered that there is no irreversibility built in. What Landau tells you is that the irreversibility is, you find it again when you linearize around a suitable equilibrium. Rate of decay is obtained by solving some complicated equation. It's an optimization problem. And the rate of decay involves the equilibrium. And it involves some complicated Fourier transform operation. This is fundamental in the behavior of the Vlasov equation. Landau damping phenomenon. Perturbations may damp away spontaneously in an apparently irreversible way. I insist, apparently irreversible. Reversibility is still there, but it's very difficult to observe because it has gone to very oscillations of very high frequency in the velocity space. It's well accepted that this damping implies relaxation in a short time before any entropy increase in real life. This is from astronomer Lyndon Bell, a galactic system whose density has achieved a steady state, so that you may have the impression that your galaxy is at equilibrium. It will still have information about its birth still stored in the peculiar velocities of its stars. Many authors have studied static approaches to this, to start to put this on statistical basis, but there is no result whatsoever about the dynamics except for the Landau damping perturbative effect, which has the drawback that it's perturbative, but which has the which is so important because that's the only thing that we have for such realistic systems to grasp something about the reversible dynamics and its irreversible effect. What is difficult here and tricky from the analytical point of view is about this approximation. Can we, so Landau did the linearization, that is the linearized equation, and it's integrable in some sense. How can we justify this approximation from the nonlinear to the linear? Linear Vlasov is integrable in some sense. This has a flavor of Kolmogorov-Arnold-Moser theorem, actually. Is linearization valid as time goes to infinity? It's absolutely non-trivial because you are perturbing the equation fundamentally as time goes by. One of these equations has preservation of entropy, the other has not. It's supposed to be quite different behavior. Actually, it was 60 years of debate before we settled this down in 2009 or 2010. taking a periodic system with an interaction potential W, no more singular than the Newton potential, take a linearly stable analytic equilibrium, which depends only on the velocity, take an analytic initial data close to F0, solve the Lazarev equation, then the force goes to 0, and the distribution function converges weakly to an equilibrium, which you don't know a priori, which is constructed from the proof, and the convergence is exponentially fast. So it does converge to some equilibrium as time goes by. No way a priori to predict it. Anything could be an equilibrium as soon as it is stable. When you look in phase space, and more easily when you look in Fourier space, you see what is going on and what you should do to recast this problem as a regularity problem. This is Fourier space. So these are frequencies. I'm in periodic geometry. So here are the special frequencies. So they are discrete. This is in frequency in velocity space. So it's continuous. At time equals 0, this is maybe my distribution function, has some regularity with some Fourier transform at k equal 1, k equal 2, k equal 3, etc. Actually, it's a lattice. And then as time goes, the effect of the free transport is to shift, or rather to shear, this distribution in the phase space. This is the exact solution. It's actually a transport in the Fourier space. And you see here that large spatial frequencies are transported into large velocity frequencies as time goes by. And they are transported all the fastest as they are large, which shows you that regularity deteriorates in velocity because you have higher and higher frequencies coming in velocity space. But it improves in the position space because all the bulk of the distribution goes far away, and the part that takes place here goes here around the small velocity frequencies, are parts which are very small due to the decay of the function. So transform your initial problem, see that the force converges to 0 into a regularity statement, but in which you don't measure the regularity of distribution function, but the regularity in the moving frame that is transported as the time goes. Let me insist that in such problems, regularity exists. We used to think as mathematicians that regularity is an artifact and that it does not really use in the physical world, that does not really exist, and that analyticity or Gevrey or Sobolev norms, these are just artifacts of mathematicians. Not true, not so in this problem. The regularity will be determinant to give the rate of decay, the thing that is physically observable. It can be measured in a way. In some of the results, the regularity will be crucial. A key step in the proof, analyzing the linear equation in which you look at the transport of the equation and the force, which is nonlinearly given by the equation, acting on a given background, here called F bar, of moving particles. And this is a distribution that oscillates faster and faster, but in a way which is controlled. How does it behave? So it's a linear equation, but not linearized. You look for an equation on the density, maybe, with some kernel telling you in Grolval style how you will control and try to get something that maybe enables you to get some exponential bound. It's a disaster if you do it. The kernel, which tells you the influence of time tau to time t, is something like linear in time, so you have a bound like exponential t squared, which is a disaster. But this kernel, when you refine the analysis, you see that it depends on the interaction of the various Fourier modes with each other. that this kernel, as time t grows, becomes more and more concentrated on discrete times, and that actually the nonlinearities concentrates on discrete times, which are kind of in rational relation to the time you are looking at. A kind of resonance phenomena in time. Actually remindful of the plasma echo experiment in plasma physics. You have a steady state prepared in your lab. You make a small perturbation at a certain frequency. Then it damps out. Then you perturb the electric field by another frequency. Then it damps out. And then you don't do anything and you observe some echo at a certain time, as if they interact in some space that you can't see, but still there is a force growing from zero to something, then to zero again. This is the echo. Manifestation of the reversibility. Echo shows you that the Vlasov equation will have nonlinearity with a delay effect. Delay is good because it gives added stability. Think of this, for instance, think of this simple equation, phi of t less than t phi over t over 2. It's a baby model in which only what occurred at time t over 2 matters. Here you have the growth t, but here is time t over 2. And the growth of this is like only t to the log t, so very slow power. In the case of gravitation interaction or Coulomb interaction, you can work out a baby model like this in which you look at the interaction between frequencies and in which what matters is the echo from frequency k to k plus 1 with again something that grows with time. And see here carefully, kt over k plus 1, this is the dominant echo. When you integrate this system, you see a typical growth like t to the 1 exponential t to the 1/3. And this t to the 1/3, this 1/3 exponent is important. First, the fact that it's less than 1 tells you that in analytic regularity you're good. But then it gives you a hint at the critical regularity that will be in this problem, which is a Gevrey 3 regularity. When you look in Fourier transform, decaying like exponential minus t to the 1/3, minus xi to the 1/3. In fact, it's like if you have a dictionary that you may work out actually a posteriori between KAM theory and nonlinear Landau damping. Okay, both are classical mechanics, but this is n equals infinity. Both are near a completely integrable system. There is some small parameter epsilon. There is statistics, but on the one hand, it's in the choice of initial conditions. On the other, it's in the statistical description of particles. Most trajectories are stable for KAM. All solutions are stable with nonlinear Landau damping. Resonances between trajectories are due to particle interactions in CAM, due to wave interactions like this frequency k and frequency k plus 1 in Landau. You can conjugate Hamiltonians on one hand. It's like you want to linearize dynamics on the other hand, conjugating nonlinear to the linear Vlasov equation. The regularity loss is finite in KM, which enables you to work in critical regularity CK. It's infinite in nonlinear Landau damping, which sticks you to Gevrey 3 regularity, at least 3. Both can be solved in a Newton perturbative scheme or with the method of Kolmogorov in analytic regularity, or Nash-Moser and CAM. Both can also be tackled, and this was obtained by Bedrosian Masmoudi-Moore in 2016 with paraproduct analysis and fixed point theory. This was developed later, in particular by Masmoudi and co-workers, in the same spirit and continuation of this Landau damping effects, adapting it to two-dimensional Euler equation near a very special geometry, which is the linear shear flow. If you perturb this geometry, will it converge to a shear flow? It has been debated for 100 years. The answer is yes, at least if the data is at least Gevrey 2 and periodic infinite setting. And there's a number of results which they have proven in the past results, including some very, very recent. Again, we've had small velocity, looking at the convergence, looking at the Navier-Stokes bussiness without thermal diffusivity. All these results, the key philosophy is again the damping which is obtained through the reversible part of the dynamics. And the tools which I was talking about, near an integrable linearized system, by reducing to a toy system, by studying the echo interactions, and by using norms which are carefully tailored for the dynamics. Okay, and let me not say more about these proofs, just conclude that applying tools then, as this has become over the past 2 decades, parts of the toolbox for studying these large dimensional systems with hypocoercivity, phase mixing, hypodipticity, very rich, as I try to show, but limited so far to very special geometries. They may be quantified over different time scales, give rise to very precise estimates, but they are so far only very particular case. In this respect, both in the finite dimensional case and in infinite finite dimensional case, we are restricted to very special cases or perturbations of these. Let me mention one again, finally, that all this was about the studying of the infinite dimensional system. Even when it is well posed, the many particle limit going from the finite dimensional to the infinite dimensional system may be extremely tricky. Friends, that is all for today. Already a lot there to chew, and I'm very happy to answer any questions you might have.
Thank you very much, Cedric. This was a fascinating lecture. We have a little delay with respect to the YouTube transmission, so before our viewers can ask questions, I will take advantage of my privilege as chair to ask you one question. At some point, you mentioned toy systems of differential equations where the phenomenon of equilibrium arises, even though the system is reversible. Maybe you could elaborate a little bit more on that. It's kind of finite dimensional toy examples of the kind of situation you're describing.
Yes. Let's say typically, imagine you have a simple coercive equation, then maybe and you have some good inequality, maybe it's linear, you have a Poincaré inequality, you may relate one norm to another. So your convergence to equilibrium is like a simple Grunwald type estimates or simple equation, which will be first order dissipative equation, differential equations like, I don't know, dx over dt is minus x or is less than minus x squared, something that goes to equilibrium. But then maybe you are able to do this only for one part of the system because you have the degeneracy. Then your other equations will not be as good as you hope, but they may be, and they will reflect the fact that you have a conservative part. But putting together these first order and second order differential equations, some of them coming from the dissipative part, some of them coming from the conservative part, you may put them together, all together in such a way that the system will be dissipative. So in a way, it's like replacing your infinite dimensional system with some infinite dimensional degeneracy, with some conservative part, dissipative part, by a system of differential inequalities such that the whole together exhibits the behavior. So it's a finite dimensional reduction in this way, but nonlinear. To illustrate this again, let's Okay, this system, for instance, this first equation, you can see the equation. This first equation is first order. It looks like the equation you like to have when you study a dissipative system, but it's degenerate. These three other equations are second order in time, not good for studying the strength to equilibrium. And there will actually be some fluctuation. But the four equations together, it's a system that will converge necessarily to zero. So you have four scalar quantities, and you have a system of differential equations, which is first order, second order. In the Landau damping, the toy system, you can see it at two levels. First, you have a reduction to infinite dimensional system, which is scalar systems, like it would be the various modes of an observable. And then you have a reduction by studying two families of norms. Main difference between these is that you don't work with fixed norm, but with a family of interpolating norms.
Okay.
Okay, I see a question from YouTube, which was transmitted from Carolina.
Exactly.
Can you please comment on the role of numerical simulation in development of this area? How delicate are these simulations? Simulations are extremely delicate, or rough simulations are easy. And for decades, people have done particle in cell simulations. You put particles, you make them collide, and you see how it goes, and so on, etc. To have good, fine simulation, it's much better to use Eulerian schemes or semi-Lagrangian schemes, but fully Eulerian schemes, they are the ones I trust best. And this does require some care. You remember the simulations I showed about the Boltzmann equation with the fluctuations in the degree of inhomogeneity. When such simulations first appeared in the beginning of the 90s, of the 2000s, specialists were very skeptical because they'd never seen something like that. These kind of fluctuations you can only capture by a very good, precise Eulerian scheme, or at least in those days, with the computers of those days, you could only capture them with such schemes. About the Landau damping, they are also very tricky to capture because of these oscillations, and it's better if you use special tricks to capture them. They are important to serve the intuition, but they do require a lot of care. Let's say that. In the same sense, by the way, that for the Kolmogorov-Arnold, the Moser situation, and so on, for the stability of solar system, numerical simulations were extremely important for the intuition and then for the theory. Oh, a very nice comment from YouTube. That is too kind.
So I share the comment. Thank you infinitely, Professor Cedric Villani. It was magnificent. I subscribe it. It seems that we don't have any more questions. So Cedric, once more, thank you very much. This was really a fascinating lecture. I'm sure it will be very inspiring for everyone watching. Thank you once again for accepting our invitation. And I really hope that, oh, we have one more question, Cedric. Can you read it?
What can we say in general about the large time behavior between solutions of some nonlinear PDEs and its linearization near some stable solution? Okay. Well, the question, if I understand it well, is about the solution of the nonlinear PDE close to the solution of the linearized PDE? The answer is no. For a dissipative equation, when you have a good equilibrium, the answer is yes. Then you have for all times your linearized solution that is close to a solution in the so-called coercive case, let's say. But when you have, like in the case of the Brasileira equation, when you have a conservative dynamics which is strong, then the answer is no. If you look at the linearized solution and the nonlinear solution, the distance grows with time. Actually, this is why some authors back in the 60s already were doubting that the Landau method could be put on rigorous footing at all. There are some authors, I think it was Bacchus, who said, we see that there is no commutation. He did not say it in this way, but in some sense, there is no commutation between linearization and large time limits. So there's a whole procedure of linearizing to catch a long time behavior may be completely false. Actually, the catch is that, yes, it does work, but your large time behavior of the nonlinear equation, you cannot deduce it from directly from the linearized behavior. Actually, let's take also an analogy with the Kolmogorov-Arnold-Moser, which may be quite familiar to some people in the audience. In KAM theory, you start by looking at some linear equation and you solve the equation like omega scalar grad u is equal to something. And you can solve the equation in toric geometry because you don't have resonance. And that is the condition that the various frequencies are not at resonance. And then it's a linear PDE problem that you solve explicitly in Fourier analysis. But having this linear solution explicitly does not help you, does not give you directly the solution of the nonlinear equation. You will construct the solution of the nonlinear equation by iteration. So the linearized equation will be the first step. Then you have a second step and you construct. Then you have a third step and you construct. And little by little, you construct your full nonlinear solution. You show that it remains controlled, but it's only at the linearized equation is just the first approximation. Then you construct and construct, and your final stage is not the solution of the linearized. And here it's the same. The large time behavior of the nonlinear equation is not the same as large time behavior of the linearized equation, but the linearization gives you a first step which is crucial to construct the nonlinear solution.
Thank you. So apparently now we don't have any more questions. It's time to thank Cedric one last time. One of the bad things about online meetings is that we miss the clapping. At this point, we would be clapping.
And even more important, maybe we miss the drink after the talk.
That's also true. That's also true. Anyway, Cedric, thank you very much once again. And I really hope that next time we will have both the clapping and the drinks and your presence here. Thank you.
Okay. Thank you, friends. Bye-bye.
Bye-bye.